Hello everybody. Second part of our charging of a capacitor would be the discharging of a capacitor. So our next topic would be discharging of a capacitor. In an RC circuit. If you recall, we had a battery and we had a switch here, and we had the resistor, and we had the capacitor. Now, as we want to discharge this capacitor, we are going to discharge the capacitor by closing the switch this way. So here I have a closed switch, and I am discharging this capacitor through this resistor. And if you want to have just this circuit, this would be equivalent with just having the resistor, and then remember you had the switch here, and then you had the capacitor here. So this would be the circuit that we want to focus on. Now, prior to discharging the capacitor, we had the charging of this capacitor, and the charging of this capacitor allow us to place a charge Q on this capacitor, and let's just say this is our charge Q here. And at time equals 0, the charge Q is actually Q initial as we start discharging the capacitor. Now, if you want to conceptualize what's going on here, maybe you would agree that if you want to do a graph of charge as a function of time, most likely the charge will be depleted as the charge is flowing into this circuit. So maybe intuitively you'll be able to see that we will have a sort of a exponential decay of the charge in the circuit. And maybe just like that, you might be able to find out that the current would have a similar graph, an exponential decay. But we are going to prove that. Now, as the capacitor is discharging in the circuit, I want you to understand the capacitor will behave like a battery. Now, if you want to write Kirchhoff's rule for this loop here, you're going to have, and if you take this as this direction of moving around the loop, you'll have a raise in the potential, and then the current is moving in this direction. So you're going to have a drop of potential over the resistor. So if you want to write Kirchhoff's rule, you'll have Q over C, which is the rising potential that you have as you go around the loop. And then you have minus R times I being the current, which is a variable in this circuit. The current is going to decay in value, and we will show that in a moment. Now, the intensity is defined as dq at dt, but I mentioned when we said how we charge the capacitor that Q is increasing in value, whereas when we are discharging this capacitor, dq is going to be less and less. So delta Q, if you want to think on a larger scale, is a negative quantity. So dq is a negative quantity. We want the intensity to be positive. So as you discharge the capacitor, you might want to remember the intensity is written like negative dq at dt. Now, with that being said, when you plug this expression in Kirchhoff's rule, you'll have Q over C, minus gives us a plus R dq at dt equals 0. Again, we want to isolate our variables, and as we do that, we will have dq over q here, and what we have on the other side, we will have a negative dt over RC here. And we want to integrate this, and we want to integrate from the charge initial is Q initial, and it goes to 0 eventually, and we have dq over Q, and on this other side we have a negative, and the time goes from 0 to t of dt over RC. But as at time t, we don't know exactly if Q is 0, so we better take our limit at t. At a later time in the circuit, let's just say we have a certain amount of charge, lowercase q, here. And obviously that would be something that we will be able to integrate easily. And on this side we have natural log of q between our limits q initial, and a later time we will have a certain amount of q in the circuit, and then we'll have negative t over RC. And when we plug those values, we will have natural log of q minus natural log of q initial equals negative t over RC, and that will give us natural log of q over q initial equals negative t over RC, and that would give us q equals over q initial is e to negative t over RC, and that gives us q at a later time in the circuit as being q initial times e to negative t over RC, which is what we intuitively got, that the q in the circuit is going to be depleted in time, and we will have an exponential decay. So at time equals 0 we'll have a q initial, and then that would be q initial e to negative t over RC. And we established in a video earlier that RC is our time constant, is our tau, and that would be the expression for q. Now we also want to find the expression for the intensity in the circuit, and we know the intensity as the capacitor is discharging. We said that would be negative dq and dt, as dq has a negative value and I is a positive quantity, and that would be if we want to derive here, we have q naught over RC, negative and negative gives us a positive, e to negative t over RC, and q initial over C is a voltage over resistance is current, so we can say that this is the initial current, e to negative t over RC. And again, the current also has an exponential decay. We have an initial current, I initial here, and then what we have here, I initial e to negative t over RC would be the expression for the current. So that's what we have. The intensity, which is a variable in a circuit, in a RC circuit, as the capacitor is discharging, would be the initial intensity, e to negative t over RC. And if we want to summarize what we just derived, the charge and the intensity in an RC circuit is decaying exponentially, and the capacitor is behaving like a battery. And I hope you can take these two concepts, decaying of the charge and the current in an RC circuit as the capacitor is discharging, and the fact that the capacitor is behaving as a battery. And that's all I wanted to say when it comes to discharging of a capacitor. Until tomorrow.